Hey everyone, I hope you are all doing well, and welcome back to the next video in our image processing series. In this video, we are going to be talking about convolution again, except this time we're going to be investigating a more efficient way of computing the convolution of some kernel on an image. So let's get right on into that. In this video, I'm going to assume you already understand what normal convolution looks like. So if you don't, we do have a video we've made in the past on that, so definitely go check that one out. So you might be wondering, well, what was wrong with our original approach to convolution? Well, if you think about it in terms of the number of operations, you see that if you have an image that's n by n, let's say, and let's say that the kernel is also n by n, right? So it's a kind of a big kernel. Then you're doing, for each pixel, you're multiplying each element of the kernel by some pixel, right? So there's n squared elements of the kernel and n squared pixels. So that's a total of n to the 4 operations, which is not really a great runtime. So ideally, we would like to get that down. And for small kernels, obviously it isn't going to be nearly as bad. So we could probably get away with the convolution we've been using before. But once we start wanting to use bigger kernels, it's just not going to be feasible to do any convolutions, especially if you want to do them in real time. So our goal is going to be to find a faster way to do this convolution. So if you look around on the internet a little bit, you might come across this theorem in math. It's called the convolution theorem. And what the convolution theorem says is that if you want to find the convolution of some function g on another function f, well then you can first take the Fourier transform of f and the Fourier transform of g, multiply them pointwise, and then take the inverse Fourier transform of all that. All right, so with that done, why don't we hop over to the code and see if we can implement this method of convolution. So very first thing we're going to do here is go up to the top, and we're going to include cmath, complex, and we're also going to define this macro called useMathDefines for some helpful constants. Over here in main, I have included chrono, which is just used for some timing, which we'll use later when we start testing our function. All right, so back in the .h file, we can declare this function called rev, which is going to take in a parameter n and a parameter a. So what rev stands for bit reverse, and basically it's going to reverse the bits of a. And what n is used for is n is basically a way to keep track of the number of bits a has. And n isn't going to be exactly the number of bits, it's actually going to be 2 to the power of the number of bits. So basically, if a is a 4-bit number, then n needs to be 2 to the 4, which is 16. So that's just a little example. And this is basically a helper function for the next function we're going to define here, which is bit reverse, or bit rev, as I call it here. And what that does is it takes in this array little a, and it produces big A, which is also going to be an array, and it's going to be little a in bit reversed order. So what that means is basically if you have some element at index I in array little a, in big A, the element at that index is going to be at rev of I, or basically the index that is the bit reversed I. So you'll see that when we implement the code. So why don't we actually do that right now? We can hop over to the CPP file and start the definitions. So in rev here, we're going to declare this max bits. And like I said, n is going to be 2 to the power of the max number of bits. So we can just take the log base 2 here. And then I'll define this reversed a variable, which is going to hold our result. So we'll be returning this at the end. And what we're going to want to do is loop through all the bits of a and check if that current bit is set. So we're going to AND it with a 1 shifted I times. And then if it is set, then we want to set the corresponding bit in reverse a. And to do that, all we have to do is or equals reverse a with 1 shifted by max bits minus 1 minus I. And basically what that does is if the ith to last bit of a is set, then the ith to first bit of reversed a is going to become set. So with that, we can just return reversed a, and we can go down to bit rev to make this function. And this function is going to be very simple now that we have defined the rev function. all we have to do is set big A at the index rev n comma I equal to little a I. And basically we're just taking the ith element of A and setting it to be the bit reverse of ith element of big A. And these functions rev and bit rev aren't actually necessary to our convolution, but they are going to be helpful when we print out some of the output of our Fourier transform. So I'm just creating them here. It's up to you if you want to create them or not. But why don't we hop over to main.cpp and test to make sure that these guys are working. Over here in main, I'm just going to quickly define these two functions. The first one here is going to make a random complex array. And notice that in here I'm using the rand function, which is inside of C standard lib. So if you choose to include this function, make sure you include C standard lib at the top. And the second function here just prints a complex array. So these are just going to be helpful when I'm testing here. So with that, why don't we come down to main and start doing our actual test. What I'm going to do is I'm going to define this complex array, little a, and it's going to be of length len. So I'm just going to define that constant at the very top there. And then we can fill it with random values. And now we'll make this array big A, and we'll call our bit reverse function to test it, and then we'll print that output. And let's see how this looks. So we'll print both of these here so we can see. We'll run it. And as you can see, they're both kind of switched around in the order. And if you actually go through and do the bit reverse of each of these indices, you'll see that this is, in fact, the correct ordering of the array. So we know that we did these functions right. And so we can move on to our more complicated functions, which would be the Fourier transform functions. So we're going to be using a fast Fourier transform algorithm, and there are many types of fast Fourier transform. I don't claim that this one is the fastest. I'm just using it as an example. Definitely, if you want to do a really fast one, I recommend using a library that someone's already created. But if you're just implementing this for fun and for a learning experience, then it's fine to use the one we are using here. So let's define these two functions, FFT and IFFT. And the actual implementations of these are going to be kind of complicated. And if I was to go into the underlying workings of these functions, it would kind of have to be a whole other video on its own. So I'm going to leave that out of this video, but I will leave plenty of links in the description for you all to check out if you're interested. But basically for this part, I'm just going to kind of walk you through the code here. So our first FFT function is going to take in our array X in standard order. And the reason why I'm specifying the order is because some of the FFT functions take in X in bit reversed order. Some of them output it in bit reversed order. So it's important that we know which order our input array needs to come in as. The next thing we do here is we copy little x into big X. And remember, big X is going to be the actual output of this FFT function. So that's where the actual Fourier transform of little x is going to go. And then all the rest here is just going to be the actual algorithm. And so the algorithm we're using for the forward transform involves this thing called a gentleman Sunday butterfly. And of course, I'll leave a link in the description to what that is. But basically, we're going to have all these loops, and we kind of divide the process of computing the Fourier transform into these subproblems. And for each of these subproblems, we're going to use these butterflies to compute the Fourier transform. And so that's what we're doing here. If you want the code, make sure you pause the video and copy this. There are many implementations of this style of the Fourier transform on the internet as well. This is just one example. And of course, there are faster versions out there, but this is the version I'm using. And of course, you're free to use whatever version you want as long as it computes the Fourier transform of your input sequence. Now, after we've done this whole algorithm, at the end here, we're pretty much done. We don't actually need to return anything just based off the kind of API of this function. But what we have here at the end is we're going to have big X, which is going to be the result of our Fourier transform, but big X is actually going to be in bit reversed order. So since our FFT function outputs big X in bit reversed order, for the inverse Fourier transform, we want our IFFT function to take in big X in bit reversed order. That way it's easy for us to call the FFT function and then IFFT function consecutively, and we won't have to rearrange any of the bits of our sequence. So again here, we're just going to copy big X into little x because this time little x is the output. And this time we're going to be using a butterfly called the Cooley-Tukey butterfly. It's another example of a process in computing Fourier transforms and inverse Fourier transforms. And this part of the code looks almost the same as the forward Fourier transform, except there's a couple differences. As you can see here, this variable called w step, the inputs into sine and cosine are now positive instead of negative. And there's a couple other changes with the variables, but the main change happens in the innermost loop, which is where we're using the Cooley-Tukey butterfly instead of the Gentleman-Sonde butterfly. Of course, another major difference occurs here at the end, where we are actually looping through the entire output array and dividing everything by n. We have to do this because it turns out the forward transform scales everything up by n, so when we go back, we need to divide everything by n to scale it back down. And then at the end here, we're going to get back little x in standard order because it turns out that this method of taking the inverse Fourier transform starts with a bit reversed and then goes to a standard order. So with that, why don't we head over to main.cpp and we can go ahead and test this. So what we're going to do here is, instead of using A to hold the bit reversed, we're going to use A to hold the FFT of little a, and I'm also going to create this little a recovered, which we're going to use in a minute here. So the very first thing we're going to do is we're going to actually use our FFT function, and what I'm doing right now is I'm using the chrono library to actually time how long it takes for us to compute the Fourier transform of our sequence. So inside these two timers, I'm going to call the FFT function, and that's basically going to be used to keep track of the amount of nanoseconds it takes to run. And then down here, I'm going to create another new array. This one is going to be called A ordered, because if you remember, the FFT function actually produces big X in a bit reversed order. So I'm just going to bit reverse big A into big A ordered and then print that so we can see it printed in the correct order. And then the very last thing I'm going to do is use the IFFT, and this is going to be done pretty much the same way as the FFT, so I'm actually just going to copy it here. And we're also going to be timing the inverse Fourier transform, and I'll just write that into A recovered, which I made up there at the top, so we can compare little a and little a recovered. So now we're actually going to use the times that we calculated to print out how long it took us to do both of these algorithms. So down here at the bottom, I'm just going to add these two printf statements. The first one is going to print how long it took us to do the forward FFT, and the second one is going to print out how long it took us to do the inverse FFT. So we're just going to print both of these out here. And with that, that's pretty much it for the test. So why don't we go ahead and run this. All right. So if you look here, you see our original sequence is the same as our final sequence. And this middle sequence here is going to be the actual output of the FFT. So that's what an FFT looks like. And then at the very bottom here, we see how long it took us to perform both of these algorithms. And the reason you see the inverse transform taking shorter than the forward transform is because now some of the arrays are already cached, so the array accesses are taking a little bit less time in the inverse transform. It has nothing to do with the actual runtime of the algorithm, because technically the inverse does a little bit more. Remember, it has to do that division at the end. So in this case, that's probably why the inverse is a little bit shorter. All right, so now that we have these two functions, FFT and IFFT, we want to define some functions that will compute their two-dimensional versions. And if you remember, we talked about how the FFT was separable, so we can actually use our one-dimensional FFT and IFFT functions to compute the two-dimensional DFT and two-dimensional IDFT. And so what these functions are going to take in, they're going to take in m and n, and this time m is going to be the number of rows and n is going to be the number of columns. And then we're just going to take in the grids as single dimensional arrays, and these single dimensional arrays will be assumed to have m rows and n columns. So now that those guys are declared, we can hop over to the CPP and start making the definition. So firstly, we'll make the definition for our two-dimensional forward transform. And since the Fourier transform is separable, we are going to be first acting on the rows and then the columns. So I left these little comments here. And one other thing we're going to need is an array to hold some intermediate calculations. So I'm just going to make that right now and then also make sure that we delete that at the end. For the rows, it's just going to be a simple loop over the rows where we call the FFT on each of the rows and put it into the intermediate array. And basically right here we're just doing some simple pointer arithmetic since the arrays are assumed to be stored in row major order. For the calls, it's a little bit more complicated, right? Because we can't just do simple pointer arithmetic at first. We have to rearrange the intermediate array into big X to become column major, and then we can do the same pointer arithmetic trick when we compute the Fourier transform of the columns. Now at the very end here, we're not actually going to get big X back in the standard order. It's actually in column major order, and it's bit reversed in the rows and then the columns. So if you wanted to print this out in the correct format, you would have to first bit reverse all the columns, then put it into row major order, then bit reverse all the rows, and then you would see it as you're supposed to see it. However, we don't actually need to do this if in our 2D IDFT we take in big X in column major order and bit reversed in rows and then columns. So that's going to be our little trick. That way we don't have to do this extra computation. And as for this 2D IDFT function, we also need this intermediate array to hold intermediate calculations, and it's also going to be separable, except this time we're going to work with the columns first and then the rows. So first we're going to do the little pointer arithmetic trick calling the IFFT on each of the columns, and then for the rows we're going to loop through all the rows, and first we put our data back into row major order inside of little x, and then we can do the pointer arithmetic trick to call IFFT on each of the rows. And based on how we set this up, we are going to get little x in the standard order. And that's going to be it for the DFT 2D and the IDFT 2D functions. So let's head over to main.cpp and test them. So the very first thing I'm going to do here is I'm going to change len to 16, and I'm going to let it represent a 4x4 grid of data. Everything else I'm pretty much going to leave the same, except I'm going to change the name of this timing to FFT2D, and I'm going to change the name of the function to DFT2D. And instead of len here, I need to pass in 4x4, which will be square root of len, comma square root of len. And if you don't want to do that, you can actually just pass 4x4 in here. In the middle here, I'm probably not even going to bother printing out the grid of pixels just because it's kind of annoying to bit reverse all those things and switch it around between row major and column major order. I'm also going to change the name of the timing variables to be IFFT2D, and I'm going to change the name of the function in between them to be IDFT2D like we defined in our image file. Very last thing down here, I'm just going to print out the time like I did before and also add a print for A, but it's going to be in that weird order as we described before. I'm not going to bother reordering it, but I am going to print it. So here we're running an example with 4x4, and then I'm also going to run this example where this 16 element data is going to be treated as a 2x8 grid of data. And you'll see when we run this here, if I get both of these Fourier transforms here, you're going to see that they're actually different. And actually you'll notice that the second element here actually isn't at all in the first one, and the second element of the first one also isn't at all in the second one. So it does matter what you put for m and n, so make sure when you're using your images you have the correct width and height in there. So now that those functions are tested and working, that's pretty much gonna cover it for this video, and in the next part we're gonna use this to do the actual convolution. So I'll see you in the next video.